My name is Vadim Korpusenko, and I'm the modern code developer evangelist working at Intel Corporation. In the next few minutes, I will tell you about resources available for you as part of our Intel Modern Code program, and how those resources can be used to learn or review and get even deeper knowledge of modern code, optimization techniques, and multi-layer parallelism. Knowing those techniques can help you to improve performance of your applications, and you will learn how to utilize all the capabilities of modern and future Intel architectures. Intel Machine Learning Zone contains the materials related to performance optimization of data science-related topics. Where do we start? Let's begin with a definition. Code modernization is a way of writing scalable code that uses multi-layer parallelism to take full advantage of modern hardware performance capabilities. What are those levels of parallelism? The first level is vector parallelism within a core, also known as SIMD, single instructions, multiple data. Operations where identical computational instructions are performed on large chunks of data. Both single-threaded and parallel portions of your code will benefit from the efficient use of vector computing, because those operations are independent from multi-threading. SIMD instructions will simply process multiple data elements instead of just one set with scalar instructions. A second level is called thread parallelism and is characterized by a number of cooperating threads, synchronous instruction sequences of a single process, communicating via shared memory and collectively cooperating on a given task and shared data. The third level is applied for large computational problems, when a cluster of machines or devices is needed, and many codes developed in the style of independent cooperating process, communicating with each other via some messaging passing system. This is called distributed memory rank parallelism, so named as each process is given a unique rank number. Developing code which uses all three layers of parallelism effectively, efficiently, and with high performance is optimal for modernizing your code. Memory traffic optimizations are also taken into account by Code Modernization initiative. Layout of data structures, access patterns, and alignment plays a very important role in the code performance optimizations. Poor data alignment for vector parallelism will generate a huge performance impact. Data should be organized in a cache-friendly way. If it is not, performance will suffer when the application requests data that is not in the cache. Granularity of data transfers to and from cache are in cache lines, 64 bytes in modern Intel architectures, and as such, if the next piece of data is not within the current cache line or scattered amongst multiple cache lines, the application may have poor cache efficiency. Efforts spent to modernize code with better parallelization are clearly an investment in the future. Quote from James Reinders. How to find more information about code modernization, multi-level parallelism, and optimization techniques mentioned so far? Well, there are several educational materials available on our Intel Modern Code Zone. 44 short videos diving into topics of code parallelization and optimization for Intel Xeon Phi coprocessors, as well as 10 two-hour-long webinars created by Colfax, covering the same topics but in greater detail with demonstration of code modification. Code samples can be used to practice your hands-on skills of code optimization for performance. The Code Modernization optimization framework takes a systematic approach to application performance improvement. This framework takes an application through 5 optimization stages, each stage iteratively improving the application performance. The stepwise approach helps the developer achieve the best application performance in the shortest possible time. In other words, it allows the program to maximize the use of all parallel hardware resources in the execution environment. What are those stages? Leverage optimization tools and libraries. Profile the workload using Intel VTune amplifier to identify hotspots and Intel Advisor XE to identify vectorization and threading opportunities. Use Intel compilers to generate optimal code and apply optimized libraries such as Intel Math Kernel Library, Intel TBB, and OpenMP when appropriate. Scalar and serial optimization. Maintain the proper precision, type constants, and use appropriate functions and precision flags. Vectorization. Utilize SIMD features in conjunction with data layout optimizations. Apply cache-aligned data structures. Convert from array of structures to structure of arrays, and minimize conditional logic to reduce branching. Thread parallelization. Profile thread scaling and affinitize threads to cores. Scaling issues typically are a result of thread synchronization, implicit-explicit barriers, or inefficient memory utilization. Scale your application from multi-core to manycore with a distributed memory rank parallelism. Scaling is especially important for highly parallel applications. Minimize the changes and maximize the performance as the execution target changes from one flavor of Intel architectures to another. So once again, for superior performance and long-term sustainability, there are three levels of parallelism programming to consider: vectorization, data parallelism; multi-threading, task parallelism; and distributed calculations, prots parallelism. And don't forget about memory traffic optimizations. I recommend you watch the short video course or full-length recording of Colfax's hand-on workshop, play with the code, and stay tuned. Be tuned.